Your search demo works, but it's not usable. We'll turn it into a real API with filters and pagination. Many projects start with a toy search box that returns something relevant, but it falls apart when users want slices or filters. By the end, you will be able to run a small FastAPI service that indexes text with Whoosh, ranks with BM25F, applies simple tag filters, and returns stable pages of results. This makes your demo feel like a product, not a prototype. I'm Professor Pi, teaching search and IR with simple Python. Search is glue between raw text and user needs. In practice, you build a search API when users need quick answers from a growing document set, or when you want an internal service that other apps can call. Whoosh is a pure Python full-text indexer that works well for small to medium collections and fast iteration. FastAPI gives you a minimal web layer to expose searches as HTTP endpoints. Together, they solve the common pain of ad hoc scripts that are hard to test and impossible to scale. At a high level, we want relevance, simple filters, and predictable pages. Relevance orders results, so the best answers bubble up. Filters let users narrow by tags or attributes. Pagination slices the ranked list, so clients can request a specific window. For a toy corpus of a few documents, this is fast and easy to reason about. The trade-off is that Whoosh is not made for web scale, but it is excellent for prototype APIs and low-traffic services. We will build a tiny FastAPI app, create an in-memory Whoosh index, run a BM25F ranked query, add a tag-style filter, and then expose a search endpoint with pagination. None of this is magic. Whoosh stores inverted lists and scores terms. BM25F balances term frequency and document length. FastAPI wires parameters to function arguments so we can accept query, tag, page, and size. First, verify the API surface is reachable with a tiny test. This snippet creates a minimal FastAPI app and verifies a working /ping route via TestClient. The code instantiates a FastAPI application in app and a synchronous TestClient to exercise routes without starting a server. A single GET route returns a tiny JSON payload so we can test connectivity and response parsing. The client calls ping and inspects the JSON body to extract the OK field. The printed status confirms the app is reachable and responses are JSON-shaped, which is essential before wiring search endpoints. Seeing status true means your API surface is alive for integration and testing. Next, build the index in memory so iteration is fast. This snippet builds an in-memory Whoosh index and writes the first document. RAM storage keeps the index ephemeral for fast iteration, while fschema defines fields, with ID stored so we can return it later. The writer adds a single document containing text in the body field and auto-commits when the context closes. We keep the schema minimal for now to focus on full-text indexing without filters yet. The printed count verifies a successful write and that your index is ready for querying. Now, we run a ranked search to see relevance in action. This snippet executes a Whoosh searcher with BM25F waiting to rank results. The searcher S is created with sc.bm25f to apply modern relevance scoring with term saturation and length normalization. Query parser turns the query string into a parsed object based on the body field in the schema. The search call retrieves the highest scoring hit and accesses the stored ID for display. If you expand terms or documents later, BM25 typically improves precision at the top ranks. Smaller K values reduce latency, but may truncate useful candidates. The printed ID shows which document BM25 considers most relevant. Next, we add a crude tag and constrain matches to it. This snippet simulates a tag filter by encoding tag data into the Whoosh text and querying with a Boolean clause. A writer adds a second document that includes a tag token inside the body, so we can constrain matching with a structured query. Query Parser builds a composite query that requires both Python and tag data. The search retrieves a small, bounded result set to keep latency predictable. Increasing limit broadens the candidate pool, but may cost time. Keep it small alongside precise filters. The printed count confirms only tag-matching results are returned. Finally, we expose a search endpoint that accepts query, tag, page, and size. This snippet exposes a FastAPI/search endpoint that queries Whoosh with optional tag and paginates results. The function collects queue, tag, page, and size, then builds a parsed query that appends a tag clause when present. It searches with a limit proportional to the requested page and slices the results to return a stable window of IDs. The TestClient calls the route, fetching the second page to verify pagination mechanics. Larger size returns more hits per page, but increases response payload and ranking work. Smaller size trades detail for latency. The printed IDs show the page slice your client would integrate downstream. This toy pipeline maps cleanly to a simple production flow. The in-memory index becomes a file-based index. The TestClient checks become automated integration tests, and the same search logic powers both web UI and background jobs. For low-traffic services, this keeps complexity low and debugging straightforward. Recap: what it is: a minimal FastAPI search API backed by a Whoosh index and BM25F ranking. When to use it: for prototypes, internal tools, or datasets that fit on a single machine. One caveat: Whoosh is not designed for very large corpora or heavy concurrent traffic. Next step: tune BM25F parameters, such as K1 and B, to shift how term frequency and document length affect ranking. That single knob often gives the biggest real-world improvement without changing architecture. If short, practical IR helps, subscribe and watch the IR videos.